Hey, AP Chemisters, this is Mrs. Vandeloy bringing you another edition of The Blank Wall. We are continuing in Chapter 1 and Section 1.6. I left off right where we filled in the blanks. We looked at how to convert between meters and centimeters, millimeters and meters, and nanometers and meters. And what is the main thing here? So I wrote, remember, the smaller unit gets the bigger value, and vice versa. The bigger unit will get the smaller value. So remember, for our answers here, meter is a bigger unit, so the one's going to be a smaller number. It ends up being 100 centimeters. Over here, millimeter is my smaller unit, so this is my bigger number, and I get 0.023 meters. And over here, nanometer is the smaller unit, so 540 is the bigger number, and we end up with 540 times 10 to the negative ninth, or 5.40 times 10 to the negative seventh meters. So that works. And I showed you last time this idea here on how to figure out how many times over. So here's my base unit, and if I'm going to go from, let's say, meters over here, I'm going to multiply to get that bigger number by how many units over I need to go. And if I need to go to the left, I need to divide to get the smaller number to the bigger unit. So let's go ahead and see what the problem coming up is next, okay? And in letter C, it says the hydrogen atom is 1.06 times 10 to the negative 10th meters. What are two appropriate representations? So let's go look at this number line and find 10 to the negative 10. All right, so remember, micro is -6, -7, -8. Nano is -9. -10, -11, -12. So -10 is right here in between the nanometer and the picometer. So I'm going to use the nanometer and the picometer as my two approximate representations here. So let's look at the nanometer first. So remember, I said nanometer is 10 to the negative 9. So the question is, how do I go from a 10 to the negative 10 to a 10 to the negative 9? Okay, that's my nanometer. Well, I multiplied by 10, didn't I? So if I multiply by 10 here, I need to divide by 10 on the first part. So 1.06 divided by 10 is 0.106. But so now I have 0.106 times 10 to the negative 9. And what did we say 10 to the negative 9 is? That's my nanometer. So I get 0.106 nanometers. Now, does this make sense? Which is my bigger unit? The meter is. So 10 to the negative 10th is smaller than 0.106, isn't it? Well, what was my other approximation? Okay, it was 10 to the negative 12th. So how do I go from 10 to the negative 10 to 10 to the negative 12? I divided by 100 here. So if I divided my power by 100, I'm going to multiply my coefficient by 100. So 1.06 times 100 is 106. And so what can I replace this by? What is 10 to the negative 12th? That's my picometer. So I get 106 picometers. And so once again, this is my bigger unit. I get the smaller number. My smaller unit gets the bigger number. Well, look even in between here, if you will. All right, which is my bigger unit? My nanometer is a bigger unit than a picometer. And notice that the 0.106 is smaller than the 106. So what would I like you to do now is do number 2 on your own. So go through the same route, and why don't you use two appropriate representations and pause this, do it, and come back. All right, welcome back. Let's see how you did. Well, if you went over here and found 10 to the negative 5th, it's right here, isn't it? So 10 to the negative 3rd, negative 4th, negative 5th, negative 6th. So my two multipliers will be a millimeter and a micrometer. So which one do you want to do first? You're going to do millimeter first? So here's my millimeter, and it's 10 to the negative 3rd. How did I go from 10 to the negative 5 to 10 to the negative 3? I multiplied by 100, didn't I? So if I multiply the power of 10 by 100, I need to divide your coefficient by 100, and I get this number, okay? And what can I substitute 10 to the negative 3 by? It's your milli, so there's your millimeter. And what was the other multiplier? This is at 10 to the negative 6. So how do I go from 10 to the negative 5 to 10 to the negative 6? I divided by 10. So what do I do with my coefficient? I need to multiply by 10 and get 55.7. And don't forget, 10 to the negative 6 is a micrometer. And I get 55.7 micrometers. And once again, which is my bigger unit? The millimeter is bigger. It gets a smaller number. And my smaller unit gets the bigger number. So start getting used to the idea of no calculators. The multiple choice section of the AP exam has no calculators. So you need to do something called mental math. So how would I do a problem like number 10 with no calculators? So once again, what should you do to do problem number 10? Well, a meter is a bigger unit than a micrometer, isn't it? So I know my answer has to be bigger than 10,000. Micro is, you know, there's a million of micrometers in 1 meter. So if I multiply 10,000 by a million, all right, what do I get? I get 10 billion, which is what I answer. Well, 10 to the 4th times 10 to the 6th, your answer is C. See how if you can get that on your own, or, you know, if that doesn't make sense to you, you know, try to work it out or ask me tomorrow. Number 2, I want to hang on to this because we haven't done the next section yet. So we'll come back and look at number 2. All right, let's go ahead and turn the page. Mrs. Vanderwall, you didn't go to the next page. You went to a prior page. You're right. I want to go back and take a quick peek at the metric system, okay? We have 7 base units. We have length, mass, time, temperature, amount, electric current, and luminous intensity. What very common unit is not in here? All right, you might recognize where's volume. Volume is not part of the original 7 units of the metric. Why is that? Well, if you're on the next page, you'll know why. Here we go. A derived unit is a combination of other units. So volume, if you remember your geometry class, is length times width times height. So if you can take 3 units of length, all right, you're going to cube them and you're going to get your volume. So the problem is with the metric, if I take the base unit of the length, which is a meter, which is, okay, in your mind's eye, close to a yard, you could probably visualize that one. And if I made a cube out of a yard and visualize that, that's a really big cube, isn't it? Well, a cubic meter is also pretty big, isn't it? So a cubic meter is not very handy. You're not going to go to the grocery store and buy a cubic meter of pop or something. You couldn't carry it or stick it in your car for most of you, okay? So this is too big. So what they decided to do is like, okay, well, the metric system is based on the base 10 system. Oh, I didn't mean to do that, but anyway. And they divided the meter by 10. If you recall, that's a decimeter. So 1/10 of a meter is 1 decimeter. So a liter is 1 decimeter cubed. Okay. Well, we don't usually talk about decimeters. Sometimes in medicine you might see decimeters, or I don't know where else. You really don't see it. We talk more about cubic centimeters. So wouldn't you know, there's 10 centimeters in 1 decimeter, and 10 times 10 times 10 is 1,000. So 1 liter is 1,000 cubic centimeters, and that's what you probably need to know. Now, what else can we look at? I'm going to go back here again. So if my base unit is the liter, all right, well, what else is 1,000th of a liter? Well, go here, 1, 2, 3, and 1,000 milliliters are also 1 liter. So if there's 1,000 milliliters in 1 liter and 1,000 cubic centimeters in 1 liter, well, guess what? This is important. We have 1 milliliter is equal to 1 cubic centimeter. So underline this, circle this, highlight this, star this, whatever it takes to know this, okay? That's a very, very important relationship, okay? We have another derived unit, and that's density. It's a ratio of mass per volume. Density equals, M divided by V. It's an intensive property. What does that mean? It does not depend on the amount of material present, okay? Kind of like melting point is another intensive property. If you recall, extensive property does depend on the amount of material present. all right, like mass and like volume, and like a few other things that we can talk about in class. Remind me, okay? So density is, again, a ratio, and you can look that up, all right? So it doesn't make any difference how big that chunk of gold is. A big piece of chunk and a little piece of chunk of gold is going to have that same density. So let's kind of calculate this, okay? All right, it says a small nugget of gold has a mass of 22.5 grams and a volume of 2.38 cubic centimeters. Find the density. All right, let's do that. So I always suggest write down your formulas, always. All right, I'll do that. And then we will do this. So here's my mass and here's my volume. I just plugged in those values, so the mass right here and the volume here, and I divided, and whoops, and what did we find now? We found that the density is 9.45. Now, what did I just say about density? Isn't it an intrinsic property? So what do you notice here? Here's a list of all these densities, and if I look down here, gold is 19.3. And if I scroll up here, I definitely did not get 19.3. So my guess is maybe you got a little bit of fool's gold going there because the densities aren't the same. If you look through here, it's like, well, what does have a density of 9.45-ish? All right, you know, you're not really finding a whole lot here on the list. Maybe copper, I'm not really sure. I don't really see anything else. So there's either a problem. It's not pure gold. Oh, could it be a mixture? Sure could be. Or, you know, they made a measurement wrong. So I apologize about that one. So problem number 11, why don't you read this, pause this, calculate your own density, and answer the question. So go ahead and pause this and see what you get. Ruh-roh. So what happened? Is this an actual platinum ring? Well, if you do the math, no, it's not. If you look on the chart, which is kind of odd as well, you end up with 13.5 grams per cubic centimeter. I have never seen a mercury ring in my life. It's a liquid, so that would make a very good ring anyway. So it's definitely not platinum, okay? So, somebody's in trouble, aren't they? So finish out the problem and do problem number 12 and see if we have a happy ending. Go ahead and pause this. All right, so if you did the math, and there you go, you get a density of 21.4 grams per cubic centimeter. Now you can compare it to this, and voila, it is platinum. Happy ending, okay? So let's go ahead and do. So we have a metal cube that has an edge length of 11.4 millimeters and a mass of 6.67 grams. Calculate the density. Now, if you go back and look at the table 1.4, what are the units of density? It's grams per cubic centimeter, not millimeters. So what did I do here? Can you see what I just did? I converted 11.4 millimeters to 1.14 centimeters. Why did I do that? So I get the same unit. And then what? Well, let's find out the density. Density is mass over volume. Look what I did here. I took this and I end up cubing. So in the denominator, what's 1.14 cubed? Take that number and take 6.67 divided by that, and I got 4.50. Okay, so what's the most likely metal this is going to be? Well, over here, I see titanium at 4.51. That's probably what it is. All right, so we made some titanium. Let's go on. So now we have the density of copper decreases as temperature goes up. Which statement actually describes it? Well, here we go. Density is mass over volume. And what did we say? Density went down. So does mass change with temperature? Not at all. That's why it's called law of conservation of mass, okay, or of matter. So what is the only thing that can change? If it's not mass, it's volume. So what will happen to volume if density goes down? Volume has to go up. It expands. So your answer is letter C right here. Mass will not change. Let's go ahead and do problem number 15. So given that same idea in problem number 14, hot air rises, notice I have the same number of atoms in this case, I have the same mass in that balloon. So what changes, that as the temperature goes up, you have more zoomies, remember those? All right, they're gonna go faster and they're gonna expand. So if the mass remains the same and the volume increases, therefore density goes down and balloons, hot air balloons go up, hot air rises, all right, all because of density. And then problem number 16, let's go ahead, we'll do that in class. And what I'd really like you to do is go back and do problem number, what was it, 11 down here that I told you to, or problem number 2. Go ahead and do that on your own, and we'll talk about tomorrow. I'm out of time, so don't wait to be great. Bye.